Luco, can we get started? Thanks. You point on one person, everyone sits down. All right, great. The first talk in the afternoon is going to be Don Syme from the Cambridge Research Lab, and he's going to talk about closures on .NET.
Okay, is that on?
Yeah.
Sorry. Yeah. Right. So, in between working on generics for the Common Language Runtime, I've been trying to work out what we should do for other aspects of functional languages on .NET, and the next thing that comes on the list after looking at polymorphism is the question of what you do for functions, for first-class function values and for closures. And this is, from the point of view of Project 7, this is a pretty real sort of problem. If you talk to people implementing object-oriented languages, they don't understand this problem of language-level interop because it's sort of largely solved now. All these things like objects, calling conventions, exceptions, and interfaces and classes and all that sort of stuff, they're sort of a common model is or a sufficiently rich model is available that C# and VB can easily talk to each other, and Eiffel and other object-oriented languages like Lightning Oberon or the component Pascal, not particularly object-oriented, but it's still a sufficiently simple language. The language-level interop story works very well for those languages. And if you extend languages like functional languages with constructs like either it's already got a exception-based constructs or you extend a language with classes, then that all works fine on the Common Language Runtime as well. Languages can all just talk to each other and understand each other's constructs. But we've got this whole list of languages here which all have some kind of notion of lambda, right? Some untyped function, of function values of some kind, whether they're typed or untyped doesn't matter too much. Haskell also has this pervasive notion of delayed computations, which are effectively a closure kind of operation. And other experimental languages like Funnel have these things. Less experimental languages like Mercury that are quite advanced. It's a typed prolog language. Also has a notion of first-class function value, even though it's not explicitly a functional language. It's kind of got a functional core subset to the language. So the question is, we've got a problem, right? Because at the moment, if you take the Project 7 implementations of all these programming languages, then a function value from one language just can't be used in another language unless you happen to know the particular encoding that's used for for function values by a particular compiler. There are a couple of reasons for this. First of all, there are differences between the constructs that I mentioned on the previous slide. Some are typed, some are untyped, for example. Some of the differences are quite subtle, and some of them just, if, for instance, interactions with polymorphism or generics can be quite subtle. But some of them just aren't subtle at all. Like Haskell is quite a different notion of closure and with these delayed computations. But even if there aren't any differences, compilers just encode the same thing in lots of different ways. And I've been thinking, well, should we do something about this and standardize how sort of function values are encoded? So this is what I want to talk about. Just make sure we're all on the same page with what we're talking about with regard to closures and function values. Talk about lots of ways you might think of encoding this down to IL, or three ways, and some variations on those ways. I'm trying to do this scientifically by actually doing lots of encodings and finding out how fast they run, and then with the hope that we can then either get the evidence to build something into the Common Language Runtime or to choose a particular encoding as a standardized encoding. And then I'll tell you what conclusions I come to from the experimental results. So here's some source language bits and pieces. I'm assuming we've all used a functional language sometime in our life. So his in Scheme, I'm not actually sure I've got the syntax exactly right, but we're applying some function value here we're passing a top-level function as a value. Here we're creating an anonymous function value in line. In Scheme, you've got this nasty thing that all arguments are really passed as S expressions, that the list of arguments is bundled up as an S expression. And of course, with function values, inner functions like this lambda, they can access the lexical scope, such as this Z value here comes from the lexical scope here, and that's why you get this notion of a closure, of course. So SML, OCaml, Haskell. In standard ML, here's another inline function value, slightly different syntax. This one expects 2 arguments bundled together as a tuple. Here's OCaml. This is, again, a typed language. These have to be integers in this case. So the types are inferred by the compiler. And then in CAML, the tendency is to write functions that return functions as values. This takes 2 arguments. It appears to take 2 arguments, but what it really is one function returns another function, which then expects another argument and then eventually does the computation. This is the style that's very commonly used in CAML. And we'll see later that CAML actually expects these to be optimized. So if you apply 2 arguments, then things will run faster. It won't do it in slowly as it appears. And here's Haskell. It's much the same thing. Haskell has its own set of issues, which I won't talk too much about today. So closures are just functions in context, where context is the environment, a bunch of free variables. Closure expressions are the things I was pointing to on the previous page. Usually the context is implicit from the free variables that just happen to be used. A function value just has to have some notion of a code plus data. In terms of implementing function values, you're just going to have some code, normally a code pointer or a set of code pointers, and some data which holds the environment. Function application, just invoking a function value, giving it some arguments. And then if you're talking about a type setting, then you have function types. So you have general class of function types A to B, type int to int, and so on for the function values. So what do we want to do? My ultimate aim is to have a fully specified encoding of closures of a wide range, or you could think of it as taking a lambda calculus, a sufficiently rich lambda calculus, and saying this is how you should encode it down into Microsoft IL. I want that encoding has to have various properties, such as you have to be able to support separate compilation, and you obviously want it not to be too complicated, or at least well enough specified. The easier the better, of course. And that helps in lots of different ways, right through from helping the compiler writer. And if the match is very close between the source language and what's generated, then debugging becomes easier, profiling becomes easier, and everything else. It's got to be fast enough. Fast enough is a very hard thing to decide in this area. So it would be nice if you could do a reasonably competitive functional language implementation. And then it needs to fit with other aspects of the design of Microsoft IL. In particular, fitting with polymorphism is important. In this area, you always have to watch out for special cases where you instantiate type variables with function types. You can often get curious interactions between your compilation mechanisms with polymorphism, but it's something you always just have to watch. Okay, so here's an example. Just this is just some sort of pseudo-functional language down below, and here's some sort of generic C# up above. Throughout this talk, I'll sort of assume that generics have been added to both C# and to the Common Language Runtime in roughly the model that we've been proposing at Cambridge. So here we go. As a function value f is passed into some generic C# code, and we're going to map this function f over all the values in this table, not over the keys, just only over the values. So there's a loop, and we do a application of some function value. This may actually be f.apply or something like that in C# code. And so we're invoking the function objects many times here. So here down below is the functional language, and Say we get an event from the operating system to process some update, and we want to update some table by mapping a function over the values in the table. And this expression here is the function we're going to map, and it's just going to do some renaming depending on the values that came in for all the different values y that come in that are stored in the table. Okay, so here's the function we pass in. Every time you process update gets called, a new closure object will have to be created for this closure expression, and to wrap up the different values of the free variables that apply each time. You basically you need a new object for this inner function each time that is called. Okay, and then when this callback, when this function value gets called from up here, you eventually call this bit of code, which eventually comes down here to the renaming. And of course, these function values, we're not dealing with a pure functional language. These function values can have side effects, such as incrementing some global counter at this point, just to get across that we're not trying to do really pure functional languages here. We're just trying to get a notion of delayed computations of first-class function values. Up here, the type I used for this function value f was a generic type, system.func, taking a values to values. That's just a way of encoding function types as generic types into a space of generic types. Okay, so here's a transformation that I assume to have happened throughout the functional language. This inner lambda here, I presume you name all of those delayed, all those lambdas. So you give it a name called clo here, and the lambda expression gets replaced by allocating a new closure object that wraps up the environment. Here we've made the environments, the parts of the environment that are used explicit, val old and val new, and then here's the name we've given to that inner lambda, and I annotate the environment that it takes through here. They're different kind of arguments. They're environment arguments, and then these are the real arguments that get processed by the lambda, and there's the body of the lambda. So we assume all closure expressions are named with the environment annotated. Right, so how do we implement a functional, these lambdas then? What sort of choices do we have on the MSIL? So we really assume generics have been added to the CLR for these implementation choices. Okay, so I want to go through some things which we don't really have much choice about. So one choice, if you want separate compilation, is these function types have to be structural, which is why I'm using generics here. If you have one type, func from integer to integer, then in one place of your program, then it's the same type as func from integer to integer, just like integer array is the same as integer array in another type in two different parts of a program. They're structurally equivalent types. You have to be able, and that's a problem with using delegates as they stand in the current runtime, for example, is that they're not structurally equivalent types. You have to actually name the delegate type and introduce a class for the new delegate type. But I will talk about using delegates a bit later on. Okay, so using these generic MSIL types seems kind of obvious. You get the structural equivalence for free. And you could build structural equivalence for delegates into the, say, MSIL. And that's been talked about in the past. I haven't yet specified what system.func is. It could be a class, a generic class. It could be a generic interface. It could be sort of a general class of delegates. So I'm deliberately leaving that unspecified because different encodings will actually use different, that will be different for different encodings. Okay, so another thing we don't really have much choice about is that function objects have to be heap allocated. In principle, you can think about sometimes encoding function values on the stack, but in general, function objects, just like just the same reason that objects with virtual methods have to be heap allocated. Where you just can't get around doing that. Okay, so these function values are going to point off to something in the heap, and that's going to have two parts: the code and the environment. Somehow you've got to be able to access the code and the environment. So you've got two choices, two things you really have to decide how you're going to represent the environment. Where's it going to be stored with regard to this object? Is it going to be in another? I'll go through the choices. The only important thing is that the relevant parts of the environment have to be accessible via these pointers somehow. And how do we store the code? How do we get at the code? How do we find out that this function value is really telling us, for example, that this function value is really telling us to go to this bit of code? Okay, so on the .NET Common Language Runtime, of course, this is an indirect call, and you've only got a few choices for encoding indirect calls. You can use classes, use interfaces, you can use delegates, or you can use C-style code pointers. Okay. So what sort of implementations can we contemplate? Well, by far the easiest thing to do is just to do the obvious encoding into classes and virtual methods. So here we've got an abstract base class, which is going to be our general class of function types. And here our closure that you saw on the previous page becomes a class which extends a particular instantiation of that general class of function types. This take an apply method, take an A and return a B, and it stores its environment in the closure object and then overrides the apply method. Okay, so that's the space of function types. Each closure becomes a class, not a delegee class. That's actually slightly wrong. It just becomes a new class. And closure construction allocates an object, and application becomes method invocation. So that's really simple. Okay, then another implementation you'll want to consider is to do much the same thing with delegates. You assume that C# lets you do a generic class of delegates. So it lets you define a parametric class of delegates which takes A parameters and returns B's. This is the class close. You still need a delegee class, which is going to hold the environment. So each closure becomes a delegee class, and it's got a method. It's not a virtual method anymore. It's a delegate method. So the delegate closure construction has to create both an environment, and then creates a new delegate, which says so the environment is wrapped up here, and then when you construct the closure object, you say, well, when the delegate gets invoked, come back to this apply method. And then invocation just becomes delegate invocation. Okay. So another way to do it is to use C-style code pointers, which the Common Language Runtime does provide, but they're slightly unverifiable at the moment. They could be made verifiable in V1, in V2. This is a question that needs to be addressed. So this is a bit different. So we have, again, a class which has a general space of function types. But instead of having a virtual method, we store in the object itself, we store a code pointer. And the fact I've used void star here is just because I could have written out the longer type from down here. But it's a code pointer. That's all we need to know. Now, the library for closures provides us. This is what I'm showing here is a library which provides not only the general type but also some helper functions. So it's got an application method, generic application method, which takes a function value and the argument and returns the value. And obviously, this is a helper method for application, which will actually just go and call this code pointer underneath. But because code pointers aren't verifiable, you're kind of wrapping up the access to the library just by giving a safe method on the outside. And So the nice thing about this scheme is you can then define a general class of closures rather than having to define a new class for every single closure. So you just have, this is in the library, and it's a closure. This class acts as a template for all possible closures that you might ever want to generate. And the key here is that, so you take an extra type parameter E, which is going to specify the fields of the environment, and you take your argument type and your return type. Now, what are these other bits and pieces? Well, this is the code pointer for the code that you want to get called as a callback, and that code pointer is going to be passed back the environment and then the argument, and has to return a B, which is a return type, and then that E there is the environment. And there are lots of tweaks on this scheme. You might want the environment to be passed back by reference. You might want multiple environment fields, for example. You might want E1, E2, E3. Or you could instantiate E with a struct that wraps up the environment, or with a tuple of values that wrap up the various fields of the environment. Okay. So the good thing here is that as long as these method pointer types are verifiable, that is, you just do a load function on the call at the call side, and then you can pass it across to the constructor. That's all you need. The rest is sort of client. So client code is verifiable, but the implementation of the module can just use unsafe tricks, just like anything else you build into the environment, into the common language runtime environment. So let's just assume the library is code signed. Okay. So there are lots of other choices, and here's some diagrams about how you end up. So you will have picked up from those various schemes that sometimes the environment ends up flat, like this. Sometimes the environment ends up being spilt to a class if there sort of aren't enough fields to hold the environment. Sometimes you store some of it in line and spill some of it. Okay. And with code in the vtable case, so in the vtable case you get a vtable, and then you get a whole lot of object methods, and you get the code hanging off the vtable. The delegates, you get objects like this, except I haven't drawn the environment, which is the delegee object. And when you're using code pointers, the code pointer is stored inline in the object here. Okay, so I'll just skip those. There's a whole nasty range of issues to do with multiple entry points, which unfortunately I don't have time to go through. I'll come back to these if I get time. Right, so experiments with different encodings. So the way I've been doing the experiments is I've extended Microsoft IL with lambda calculus-like constructs with sort of, just as you can have classes, you can have closures, and which is what I mean by Microsoft IL plus lambda here. And I then translate those away by a bunch of different schemes. First of all, I translate away other constructs from extended IL, what I'm calling ILX. And then there are various different translations of lambdas. And then sometimes I translate away generics, which I've denoted by this for all sign. Translate everything away down to Microsoft IL, or if it's a generic common language runtime, then I'll use sort of come off here and just run this code here. So I haven't got enough functional language compilers implemented targeting ILX to do real benchmarks, unfortunately. So I've come up with a simulated performance load of what I reckon roughly corresponds to the indirect calling aspects of a typical OCaml program. So created a whole bunch of closures, 80% of which only take one argument, 15% take two, the rest take three. Some of the ones that take 2 and 3 do things after getting the first argument. They then have some side effects and then continue to take further arguments. And then I choose a range of numbers of free variables. 60% have 1, 0, 1. Well, you can see the percentages there for free variables. And then all the calling I'm doing is indirect calling, applying function values. And then there's how many instances of each closure you create and how many times you call each instance. That, which I just do this by sort of some of them I only call once, some of them I call tens of thousands of times. It's sort of a pretty random rate.
What do you mean with 80% take one argument so that you don't have currying? Is that?
So they're different types. Yeah. So 80% of the closures have no currying at all. They just take one integer argument.
And that's typical, or that's what you...
I think a lot of... So mapping is one of the most common uses of closures, and that just takes one argument to map over a data
But
structure.
usually you map a curried function over something. Like,
Well,
you do add one.
Add, yeah, in Camel you don't tend to do that quite so much.
Oh, okay.
Or the compilers will often arity raise, or change it. Will actually explicitly put in a delay. We'll change that. Yeah. But in source code in Haskell, you do that a lot, but you don't do that as much in Camel. Yeah. Okay, so let's see what actually happens. First of all, let's start with delegates. As delegates are, in a sense, the best thing. You'd really like to use delegates because it's the notion that's closest to closures on the common language runtime. So, unfortunately, yeah, there are big problems, right? Here you can see immediately that delegates, just comparing on the right, you can see call delegate versus call vert. And the times, don't forget the best time was that I eventually get to is 11 seconds as well. That's for a different scheme. Down below you can see different flavors of code, whether using generics or monomorphic code. So I do go through, I run the code both as a generic code and also by compiling everything down to object, which is this monomorphic code, and putting in lots of casts everywhere. Boxing and unboxing and that sort of thing. And whether you're taking tail calls or not taking tail calls, it doesn't really matter. Delegates are just a lot worse than using objects and apply methods. So there are known performance problems with delegates on the runtime. So these figures, you could expect if they fix those sort of known issues, they would end up roughly the same. Except, yes and no, because there's actually two objects being created for every closure value in the delegate case, because you need both the delegate object and the environment, except in the case where there are no free variables, where you shouldn't need an object for the environment.
But you haven't considered changing the delegate constructor to be more permissible, so that you don't...
No, I haven't done that yet. So there are optimizations and changes, which will definitely bring that figure down. I think you could get delegates down to the 11 seconds with appropriate design changes. Okay, so right, so this gets me to... I went through those compilation schemes and got to the one with code pointers. But what you sort of really want to do is not just have one code pointer in the object. You want to have several code pointers in the object, which correspond to slightly different calling conventions for the closure, effectively. So, and one problem is that different functional languages use multiple entry points into a closure in different ways. For example, Scheme has to bundle up its arguments as an S expression in principle. It says, here's the two arguments I'm applying to the closure. Let's create allocate an S expression, pass it across, deallocate it. Now, you don't want to do that in practice. So what you're going to have to do is have another entry point for the case where there are exactly two arguments being applied to the scheme, to the closure. And so these multiple entry point tricks get you big performance gains for functional languages. I've implemented one multiple entry point trick, which is suitable for camel code, which is if you're applying a curried function with 2 or 3 arguments, then it will jump to exactly the right code. So this shows you the benefit of having. This contrasts the 3 things. You have call virt, which is where we were at the last time if you use a virtual method encoding, call pointer, which is where you have one code pointer stored in the object, and call to pointer, which is where you have a multiple entry point trick being played. As you can see, whether you're using tail calls or not, this is on a generic common language runtime. The two pointer schemes are worth it, even though the benchmark I'm using doesn't particularly have that many closures which take 2 or 3 arguments. So it's not getting huge benefit from this. Call virt and call pointer are approximately the same. Okay, let's compare generic code versus monomorphic code, just to show you that generics is giving you a big win. Generics is on the left and monomorphic code is on the right. That shows you we're passing integers across, and if you the benchmark is always passing integers. And in the monomorphic code, you have to pass those as objects because every function becomes a function from object to object, and so there's lots of boxing and unboxing going on. And so as you'd expect, generics gives you big performance wins for this sort of thing. Let's just compare this is just the call pointer versus call to pointer. This is just single entry point versus multiple entry points. And this shows you that multiple entry points for this does gain you something in each case. No matter, the options along the bottom they're just showing that in each case it's gaining you something. The options along the bottom are various ways of representing the environment, which I'll just get to now. In this one, we're looking at, should the environment be stored inline in the closure object, or should it be stored out of line? Should you have flat closures, or should you have 2 objects for your closures? You can see the difference isn't so huge. The spill tuple is the case where it's inline, so you have flat closures. And in certain cases, you do get benefits. But even call to pointer here and here is the important one. It's not a huge benefit. I was a little bit surprised at that one. I might do more investigation as to whether that's actually right. It could be that the environments aren't big in this performance benchmark that I'm running, but that's in functional languages. The environments aren't always as big as you might expect.
But do you always have this choice? Can that depend on whether you allow side effects on the environment or not?
That's right. So a language which allows side effects on the environment has to store it out of line. Yeah, they can't store it in the closure. So it doesn't. But they can do that by instantiating with references. Finally, I think, sorry, 2 more things. There's a question of whether, I said you could have multiple environment fields, and on this benchmark that doesn't get you anything at all. This is 0 to 4 is one where you have a range of environment fields, and the one below is where you only have one environment field for the closure templates, and that doesn't get you anything at all, which I was surprised at again, but maybe it's just the particular benchmark. So, finally, verifiable code versus non-verifiable code. Just this actually isn't a particularly meaningful benchmark, so I'll skip that one. It's just whether the client code has the casts inserted or not, but there's not a lot of casts that need to be inserted for the generic code. Right. So, conclusions that I get you from that, it's pretty obvious that delegates and tail calls kind of suck on the version 1, but that's known by the Common Language Runtime team. That's for indirect calling. Delegates are a fine thing to have in C#. I've got nothing against them, and they are a great abstract notion, and the asynchronous stuff that comes with them is really, really good from a programming model point of view. I'm just, for the purposes of compiling functional languages. So generics are really useful for this purpose. Multiple entry points seem to be worth it. The hard choice is defining what set of entry points you're going to allow. Flat closures are worth it in certain cases. And this last one, multiple environment slots, didn't seem to be worth it. And finally, there are many, you could think of now taking this information and using it to modify delegates to do all this stuff. But if you can't, if it's decided that can't be done, then you can do a library-based approach like the one I've been doing, as long as function pointer types are sufficiently verifiable. There's a whole bunch of related concepts, delegates, inner classes, objects, method pointers, and so on, which I can't really go into today. But if looking forward, I want to continue to do this for real programs and implement it, say, a scheme compiler that targets this, and ML and a Haskell. We've already got a Haskell compiler, which isn't, unfortunately, in a sufficient state to get benchmarks from it at the moment. But if you were going to modify V2 delegates, then you'd sort of take V1 delegates, you'd do the basic performance improvements, you'd allow the ability to delegate to other methods besides in the class that holds the environment, you'd allow the environments to be stored inline in the delegate, and you'd perhaps look at doing some multiple entry point tricks for implementations of delegates that would particularly suit functional languages.
So most of that is on the list, actually.
Most of it's on the list, yeah. Yeah, that's great. So that's actually the end of the talk. So I've run out of time. Sorry.
So 11 seconds was the best of your measurements, or was it what you get with the Camel native compiler?
No, it's the best of the measurements. I only did the performance benchmarks a couple of days ago, and I've been meaning to do the Camel compiler. Unfortunately, it's I have to be careful because the Camel compiler might be doing higher level optimizations, which are getting rid of the closures that I think I'm creating. So I've been trying to think over just yesterday about how I was going to stop the Camel compiler doing those optimizations so I could do the performance tests. But I wouldn't be surprised if the Camel compiler was 3 seconds or something like that, 4 seconds. But we'll see. I'll try and do those performance tests over the next week. Yeah.
So I have 3 questions. So one of the things, like in Haskell, where functions are pure, so when you have an impure function, you have to wrap it in the I/O monad, and you get a lot of things which I think that blurs your measurements. Probably, I'm not sure.
It's hard to tell. Yeah. And the delays, the thunking delays in Haskell are definitely a problem. The fact that the function value itself might need to be computed.
Well, there are 2 things: it's laziness plus, purity.
Purity, yeah. So the purity just gets. I mean, the way I'm compiling closures is very close to how GHC actually compiles closures as well. So its I/O monadic actions all become functions as well.
Yeah, but there it's recorded in the type.
Yeah.
And you don't show that. And the other thing is Latrax.
Right.
Looked at that.
Yeah, so you have to have mutually recursive closures and environments. So you can store into the environment fields. The model lets you mutate the environment whenever you want, in principle, but a functional language compiler won't actually do that. So after creating the set of mutually recursive closure environments, you then fix them up to point across to each other. Yeah. Is that 2, 3?
Yeah, well, the purity and the laziness.
More questions?
Do you look at continuations?
No, you mean implementing continuations. Did you hear Nick's talk?
No, I didn't get a chance.
Yeah, so Nick gave a talk on should we add continuations to the common language runtime, and so he'll give you that talk again.
Okay.
It takes a minute.
Or it's on the streaming video. So.
Super.
Any more questions? So.
Sure, that's fine. That's right. Okay, it'll be probably shorter than that. So.
All right, great. And the next speaker is Mike Barnett, who's here in research in Redmond, and he's going to talk about verification in .NET.
Okay, the first thing I should say is that I'm not Wolfram Schulte, although I do work with him, but he's sitting over there, so if you have any questions for him, I'm sure he'll answer them. And runtime verification is work that we've been doing for a while. It's based upon the work that our entire group is doing, the Foundations of Software Engineering. A better name for our group is Specifications Are Us. So we do lots of work with specifications for software and software components. But today, the only thing I'm going to tell you about is our work for runtime verification. So runtime verification is a combination of testing and verification, program verification. And whenever you hear those two words together, it probably brings to mind the fact that they don't sound like they should go together. This is an old quote from the Devil's Dictionary of Data Processing, although I couldn't find the exact citation. So the thing we're interested in is the ability to apply a formal model to software, even though you may not be able to prove beforehand, statically, that the code you write corresponds to that model. What we'd like to do is at runtime constantly monitor the execution of the software to make sure that it does correspond to the specification that exists for it. So the place we always start is the fact that specifications are good. We believe that people should write specifications. And generally, when you tell people that, they say, yes, I agree, specifications are good, but then you have to wonder why nobody ever writes them. And the reasons we've seen are that specs are pretty useless. Most specifications are written in human language, and often they're written after the fact, after the code's been written. Even when that happens, the code continues to evolve and the specification doesn't. And it's difficult to make formal specifications using techniques that a lot of people in the research community have wanted specifications to be written. And it's difficult to use that for many real-world components. They can be done for small systems, but it's difficult to do for large, complicated software systems. However, some people do write specifications. For instance, programmers write assertions. So maybe they don't write a lot of assertions, but programmers do write assertions, and that is a form of specification. I'd go further than that. I would say actually programmers write a lot of error-checking code. And error-checking code is a form of specification. It says what things need to be avoided when you're using somebody's code. And they write exception handling. So they write specifications of what to do if the code is being used incorrectly. And of course, the real fact is that programmers write code. And code is a specification. Usually if you're given a system and you want to understand it, you end up having to really get the source code because that's the only way you can figure out what the system is going to do. Our lesson that we take from this is that it's not bad to think of code as a specification. It's just wrong to think of it as the only specification that should exist. The problem with it is that it's too low level. If there was a way to write specifications that were like code but at a higher level, so you could ignore the inessential implementation details that don't give you the information you want to figure out the behavior of the code, then you'd have a way to have a good formal specification. So we want specifications that are at a higher level than what you would get with source code, and also that are separable from source code, so that a client could get the specification and without having to look at the source code would be able to understand from the specification what the code actually is going to do. And where runtime verification comes in is once you have that, we would like to make those specifications enforceable. Our belief as a group is that all of this is possible if you make your specifications executable. So as you'll hear later in the talk, we've created an executable specification language called ASML. But before I get to the details of ASML, I want to show you our big picture. The current world lives on the left-hand side of this picture. The current world, there are interfaces. If you ask somebody what the interface is to their component, it's possible to get an extremely precise document, usually an IDLE file or a type library, some form of machine-readable formal text that tells you exactly what methods are callable in their component. And you understand how many parameters each method takes. You understand the types of the parameters. Sometimes you even get information about exceptions that are thrown. The problem is that you get nothing about what the behavior of the implementation is. You only understand the syntax. our belief is that a specification should constrain the semantics of the interface. In other words, if you had a specification, you should be able to know what the meaning is of using the component without having to get the implementation. What we're attempting to do is to be able to create from such a specification a monitor, and a monitor is just the runtime equivalent of the specification. It's the enforceable part of the contract. The specification is supposed to be the contract by which the implementation abides. And the monitor is a machine executable form of that that can be run against the implementation to check it and guarantee that it is conforming to the semantics that the specification promised. If you have any questions, feel free to interrupt me as we go. Let's see, anything else to say about that? All right. So the first point that I want to make is, first I'm going to be talking only about the monitor. So I'm going to ignore the specification for now and say, if we had a monitor, how could we use it to check the behavior of an implementation at runtime? And then the second part, I'll talk about how we can generate monitors from a specification and what our sort of specifications look like that we produce. So this builds on previous work we did outside of the .NET runtime. It was work that we did for COM components. And what we did was, using the language that our groups created, ASML, we allowed you to write a specification in ASML of a COM component. And the ASML specification would expose exactly the same interface that the COM component did. Our monitor was then a very simple, automatically generated SPI that acted as a proxy so that any calls from the client that were directed towards the component were intercepted and were delivered both to the COM component and to the specification. The calls were made on both the specification and the implementation, and at the method boundary, when the return results would come back, they would be checked to make sure that the implementation had returned results that were in conformance with the specification. So the good points about doing it this way, besides the monitor being incredibly simple, was that it gave you observational equivalence. From whatever the client could perceive, as far as the client could tell, by its interactions with the component was behaving the same way the specification said it should behave. The other thing that was good about it was that no instrumentation was required. So we could just snoop on the wire between the client and the COM component and observe all the traffic going back and forth and control the execution of the specification. There were some large drawbacks, though. We believe strongly that specification should be non-deterministic. There should be things that are left open to the implementer to make decisions about how the execution order should be in certain cases where it doesn't matter in terms of the results. And that non-determinism is hard to track when you're sitting outside the two components and treating them as black boxes. So in other words, if the specification here says that any one of a range of objects could be returned, and the implementation returns some particular object, it becomes very complicated to track the behavior over time to make sure that the object that is returned from the implementation behaves like any one of the set of objects that are possible to have been returned from the specification. Another difficulty is that most components have callback interfaces, so that a client can register its own code with a component and says, upon certain events, please call this code. That means that methods in the component, in the implementation component, are no longer atomic, because in the middle of executing it, it may call back out to the client, and the client then is free to call back into the component and observe its state or perform further state transformations. And this simple-minded architecture that is that's diagrammed here does not provide for that. It has to treat, since it's treating the implementation and the specification both as black boxes, it has to be able to just call one as an entire atomic method. And so callbacks break that model. And the other problem is that you can't, because we're treating both the implementation and the specification as black boxes, you can't look inside, naturally, since they're black boxes, to see whether or not, if the specification says more than just what should be returned from a method, but says what sort of state the implementation should be in, then it's difficult to enforce that. Okay, so that's where we were. This was the state in which we'd gotten when we started thinking that the .NET runtime provided us the opportunity to solve a lot of those negative problems, a lot of the drawbacks that our previous architecture had. Namely, since we have the capability of actually rewriting the IL and intercepting the IL, we could use a tool like Vulkan, or which is our current approach, to take the IL that comes from the implementation and to combine it with the IL from the monitor in such a way that what's really getting executed is an interleaved part of the implementation, part of the specification. And interleave it in the appropriate way so that we can see inside of the state of the implementation and so that we can monitor the callback structure and protocol behavior of the calls back and forth between the client and the implementation. So this is the 20,000-foot view. Let me give you an example to show you exactly what we're talking about. So I'm trying, the color coding here is supposed to enforce the fact that brown is the interface, the yellow is the implementation, and the blue is supposed to be the monitor. So suppose there's an interface that has a square root function in it that takes a double and returns a double, and there's some implementation that implements that via some algorithm that I don't care about right now. It's certainly possible to think about a monitor which says the two things that should be checked are the contract that must be enforced when using the square root method is that when you call it, you should always give it an argument which is non-negative. And when it returns, it really should give you back the square root, ignoring the fact that you can't actually get the precise, perhaps you can't get the precise square root, that there's an epsilon there. It's easy to see that that sort of contract, a simple precondition and a simple postcondition, can be interleaved with the body of the method. So now this is an example of how good your vision is, because what you're really looking up there is the IL, not the source code. So what I'm showing you, of course, is the source code because it's much easier to read, but where this really takes place is at the IL level. So clearly, if we take the method and we add a new local variable, we can check the precondition. We can execute the body of the original method where it's been modified, so instead of returning, it stores the value it was going to return in the local variable. We can have a postcondition that checks the contents of that local variable, and then we can finally return that. This idea has already been explored in the context of other virtual machines. So there's a lot of work that people have done for Java where they've done exactly this and had different implementation techniques for rewriting the Java classes at load time to insert these kinds of pre- and post conditions. So what I'm showing, in a sense, this is very old work that it's already been done for Java, and we're currently implementing it in the .NET runtime, but it's pretty standard. And that kind of monitor language lets you talk about things like preconditions, postconditions, class invariants, things that should be checked at the beginning and the end of every method in a class to preserve the state, to make sure that certain state invariants are maintained by the operations, and even what to do when an exception is thrown, perhaps certain recovery code that restores an object to its to a known state before the exception is released back out to the client. But we are proposing to go beyond that simple monitor language to handle things like callbacks. So certainly properties of a component you can talk about with just pre- and post conditions, but to talk about the protocol that must go on when a callback is made, that requires additions to this monitor language that I'm showing you. And so we add the idea of a mandatory call, which is a call that the implementation must make. It may do more, may execute further functionality, but it must at least make this sequence of method calls and exceptions, and being able to handle model state. We want to be able to add new fields, have state that lives only in the specification level, and not always have, in these sort of monitors, everything is talking about the actual state of the implementation. But it may be that you have an abstract state in your specification, and you need to relate that to the state of the implementation. Okay. So now if you believe me from there that given a monitor we can try to rewrite it in such a way that it is interleaved with the actual code that gets executed of the implementation, the question becomes one of where do we get the monitors from? Certainly they can be handwritten, and for the kind of example I showed you, it's clear that it's pretty easy just to sit down and write that. But it turns out that if you want to specify more complicated properties, it's much easier to do that at a higher level and then have an automatic translation that compiles it from the specification language down into the monitor. And the particular path we're following is to write specifications in ASML and then compile them down into this monitor language. So briefly, I won't go into a lot of detail. You can see our group's website for a description and a free implementation of the language itself. But it's based on work that our manager, Yuri Gurevich, started back when he was at the University of Michigan called abstract state machines. And this is a particular implementation of the theory of abstract state machines. It provides readable, executable, testable specifications. As I tried to indicate earlier, it can be used in a variety of ways in the development process that are beyond the scope of this talk. And it combines mathematical concepts with object-oriented concepts, component-oriented concepts, to give a language that we feel is really an industrial strength specification language that can be used for large product group sized components. We've used it so far in some case studies to model the debug services of the .NET Runtime and the network configuration engine inside of Windows, and found that it seems to scale well, not just for toy systems. It's currently integrated into Visual Studio 6, and we're working on porting it to become a .NET language. Yeah?
What does that mean, integrated into Visual Studio 6?
It's integrated into what exists of a project system in Visual Studio 6. So if you install ASML, it means that you can say, I'd like to create a new project, and one of the options it gives you is to create an ASML project. It will give you essentially the make file to build the project and some skeleton code that then you can start filling out. Currently, you can create a console application, a Win32 application, a COM server, or an automation server, because ASML has native COM bindings.
So it's as if it's another programming language as opposed to integrated in a way that could create monitors or that sort of thing like you were just describing.
Right. So currently, the idea is that ASML lives in this world, the world of specification, and a monitor is a specialized form of a specification which has been compiled explicitly to be integrated with an implementation so that when they run together, it checks it. But you can also run an executable specification. I should have said this before. An executable specification can be run by itself as a standalone. So you could use it as part of the development process. Say, our experience is that it's much easier to write a specification than the full implementation. And so at the beginning of the design stage, you could write a specification and play with it or drive your test scenarios against it to see if it does what you expect it to do before you ever start the coding effort to create an implementation.
When you were designing ASML, did you think about rapid prototyping? Like, did you add features to it that might be orthogonal to specification, but that would help in that rapid prototyping effort?
Okay, so the question is, did we think about adding features that would be applicable for rapid prototyping as apart from specification? So I guess I'm not sure what kind of features you would have in mind that you see as distinct between the two. So Because I guess my feeling is that rapid prototyping is a very good use of the specification language.
Well, for example, a runtime feature that is helpful for rapid prototyping is not an interpreter available.
Okay, so no, right now, okay, so it does not have a separate interpreter. It does just compile down the native code. So in that sense, no. Yeah, that's true. Okay, so not an interpreter. Yes?
I don't quite understand why this is a specification language. Why not just make it a language and compile that efficiently, and then you can do all your other nice stuff?
Okay, so the main goal, I mean, in one sense it is just, okay, the question is why call it a specification language? Why not just say it's another language and use it for everything? Is that fair to say what your question is that?
Break that up.
It is really, in one sense, it is just another language because you can write in it. I mean, it's a programming language. You can write whatever you want in it. The goals of a specification language are different. For one thing, you're not so concerned with ultimate implementation efficiency as you are with clear semantics and flexible notation and flexible features. So, for instance, yeah. So let me. No. So, for instance, there's two core features of ASML that we think are appropriate for a specification language that we think are not really appropriate for an implementation language. One is non-determinism. So there's non-deterministic constructs built into the language. I don't think that's appropriate for an implementation because an implementation is all about saying, here's what really should happen. I want to make the most efficient choice of the behavior that this thing should do. A specification is, its purpose is to say, here's the range of behavior that's allowed. I don't really care how it's done as long as the result is what you want it to be, is clearly defined. And you want to leave open the possibility of multiple paths for the implementer to decide that they want to take to get from the initial state to the result. So that's one thing. The other thing is that we believe very strongly that in specifications it's very good to have as large a granularity size as possible. So the language is in essence a parallel language, and what you specify are your transactions. So you say, in one step, here's all the updates I want to happen in parallel. And by reducing the number of steps you have for any one method that it has to make, you make it easier to analyze the model and to perform mechanical transformations on the model. And again, those are things that you don't really need in an implementation, but it avoids unnecessary sequentialization that you end up performing when you do an implementation. Yes?
Well, there are languages that have both features, both of those features, and can be compiled reasonably efficiently.
Yeah. Well, we believe if you try out our compiler, I think you'll find that the code runs, we think, reasonably efficiently. The goal is not to make a language that compiles so efficiently that we're trying to tell you to throw away, whatever other programming language you're using. So the goals are different. But it certainly runs fast enough so you don't go to get a cup of coffee while it's running and have to come back later and see it. We think it's fast. You'd have to try it to let me know what you think. Yeah.
I'm confused about something that you said just a minute ago. I'm hoping to get you to elaborate a little bit. You said, if I understood correctly, that the monitors were useful and could still be run on their own without the regular implementation.
No.
Is that wrong?
Yeah. Okay. So the question was, can the monitor be run on its own without the specification? Oops.
The specification. Obviously, the implementation is needed.
Right. So the monitor is a specific. In ASML, the specification can be run standalone. You can just run it as a separate program, and it just behaves however you've written the specification to behave. The monitor is a form of that which executes the parts of the model that are needed so that at the right points in the implementation, the checks can be made to say, yes, the two are in conformance. So that was very simple. Oops, where did I go? Yeah. In this world, that was extremely simple because we actually didn't change the specification at all. The monitor, all it had to do was call the specification and say, please execute method F for me. And when it came back, it said, okay, now I know what method F in the model should return. It returns 3. And then it checks the implementation and says, oh, does the implementation return 3? Oh, yes, that's good. Okay, we'll keep going.
Okay.
But now we need to modify the specification and compile it into a form so that it can be interleaved with the implementation. Because you can't just treat it as a black box because of these features that I've indicated on this slide that make that model break.
Yeah, but you had a sample specification for square root that said, the input was non-negative and the output was with an epsilon of
right.
Square of the output was with an epsilon of the input. If the specification doesn't know how to compute square root, it can't produce result.
Exactly.
Right?
Good
So
point.
in what sense can the specification be run by itself?
Okay, good point. So the question is, in this example that's here, how can you run that by yourself? And that's exactly the point. So you notice there's a big hole on this slide in the upper right corner. So I'm not showing you the specification. I'm saying, here's a monitor which clearly cannot be run on its own. As you point out, it doesn't know how to compute result. All it can do is that if you insert it into the implementation, it can check to make sure that the implementation did the right thing.
So to complete that picture, you would need a specification of square root that could actually produce an answer, but perhaps would not be what you'd want to use in practice because it's too slow.
Exactly. So the question was, you would have a specification that says how to compute it, maybe, but with some other algorithm that's not the one you'd want in your implementation. Right, precisely. And from that, we would derive this sort of contract, this sort of monitor that you see here. I'm sorry, Don?
The language used for the monitors, I mean, your internal representation or whatever else, the compiled representation, is it very close? Is it closer to the ASN?
No, you can think of this monitor language as C#.
Right.
I mean, we're happy.
Well, but that doesn't. Well, I mean, C#, but you've got to be able to interleave the two. I mean, is it always just interfaces with? I mean, is it exactly as you've got it written here, or is it kind of? I mean,
well, okay. So one answer to that is it really will be C#. What you're seeing here is just we don't have it fully designed in terms of. But it will be something that compiles down to IL, so that you can insert it. Remember, it's the IL that gets rewritten, not the. All you need here is.
So you just happen to be using IL as a representation for it, but have you kind of got a definition of the monitor list? For example, if I wanted to take some other specification language, such as a richer type system, say the stuff that Rob DeLine and Manuel have been working on, for example, to do key checking, and you wanted to do those checks dynamically. How would I be able to judge if your monitor language was sufficiently rich for me to compile that specifications into?
Right. Okay.
And have you got a specification for the monitor language yet or not?
No. Okay. So the short answer is we have not specified the monitor language sufficiently precisely to give you an answer to that question.
And do you have a picture as to what the monitor language is? I mean, in your heads at least, you have, or is it something you think that will evolve over the next year?
So the idea is simply that the monitor language is just, let's say, it's just C# or even VB. It must be a CLR language. And the trick that you actually do is that you use naming conventions. Naming conventions that link the real implementation against the properties that you specify in the monitor. And this Vulkan tool is just that you take the real IL, so to speak, and then inspect what a class, which interface it implements, and then you look up whether you have a contract for this interface, and then you merge the corresponding codes.
So that's fine, but it seems like you might want something much more general than that. For example, you may be able to want to insert stuff in the middle of methods, in the middle of loops. For instance, you may be trying to constrain quite a functional language which gets compiled down in some very optimized kind of way and inlines everything itself and munges stuff around. So
currently, this is just, you can think about pre-post conditions, so about this way, but actually Mike will show you that you actually can check callbacks with this specification method if it's coded in the appropriate way, and Mike will show an example.
I think Don is... You meant Don, right? Yeah. I think he's trying to get at this higher level point, which is that this technique, which I think is wonderful, by the way, and I'm all in favor of it, it leverages a common type system, and it's limited by the common type system.
IL.
Yes.
Okay, so you can only express specifications that you can type.
Yeah.
Okay, so you can't go in there and say, hey, I've got this Haskell type, or I've got some kind of type that was done in ML, like a signature thing, and expect to create specifications that address it, because you can't actually describe it in your implementation language. So is that
sort of, or you may want to? Yeah, there may be a naming problem of how the ML types have been encoded down. There may be the fact that inserting the probes may have to go in the middle of methods or in places where you don't. This is fine when you're just thinking about specifying just C# boundaries, but it may be that,
okay, so
you want the monitor language to be something much more general.
In addition to the type mismatch, there may be an execution model.
Yeah, well, this is clearly only going to let you insert probes at the start of methods, at the end of methods, and add state to classes and so on. All that stuff is great, and it fits when your source language is very close to your compilation model. But maybe you want to evolve the monitor language to be a much more general way of annotating IL, of probing IL code, and then you've got a very general tool which might be reused in a lot more settings besides ASMs or C# specifications.
Well, I only have a couple minutes left, so let me just zoom forward here and then take the rest offline. So a standard paradigm that illustrates callbacks is the subject view paradigm, where there's a subject that holds a piece of state, and whenever the state gets changed, then it needs to notify each of the view objects who have registered previously with the subject as being interested in notifications about changes to the state that the subject holds. And this is the classic callback scenario. So you have a subject. So now you're seeing this is a little bit of ASML syntax. Subject is a class. It holds a piece of state. It holds a set of of references to components that support the iView interface. It has a get method which returns the value of the state that it holds. And it has a set method which, as I said, the language is parallel, and we try to make it very heavyweight to specify sequential steps. So instead of just a semicolon, you have to say, that I want to have a sequential machine here that will first update the state, and then after the state is updated, then we'll notify all of the views through their update method. And what Wolfram was trying to indicate before is that from this, we can derive the appropriate pre- and post conditions to check, even though this behavior about updating is taking place, you can think of it in the middle of the method, we can still derive pre- and post conditions that will check these properties. For instance, that the notify has been done after the update. That since for all is a parallel construct in ASML, that all the views see the same state. That they all, when they get notified, what they will see is the value X sitting in the subject. And that this update is a mandatory call. It's one that every implementation must make, and it must make once for each of the views that have been registered. And then now this is, if you thought the rest was hand-wavy, this gets even worse. This is not what really would get compiled from such a specification. This is not the real monitor, but it's just to give you an idea of the kinds of things you need to be able to say in the monitor to be able to check the implementation of that set method. So for instance, you need to know that at the beginning of set, you need to know what are the mandatory calls that will need to be observed. Well, it's the set of v.update calls for all v that are sitting in the views set. The body of set still has to perform its update. So this is an actual statement, not a predicate. The post condition is that, well, we better have seen all of the mandatory calls. And the way to check in the middle is that when each update call is made, then it can check, oh, the state better be exactly what the specification said it should be. And when the update finishes, then it can remove that particular component from the set of mandatory calls, signaling that it's been seen. And so I just want to summarize by agreeing with Don that our monitor language is certainly not set in stone, and I'm sure we will be changing it over as we work on this project, and that we do foresee being able to use the monitor for other purposes besides compiling specifications down to it. And we want to also stress the fact that we will be able to at least generate these monitors automatically from the ASML. which allows you to incrementally add specifications to your system and does not require heavyweight verification technologies like model checking or theorem proving. And I'd like to invite you to try out ASML by going to our website, installing it on your machine, and giving us feedback on what you think of it. So, thanks.
Any questions?
Yes.
Yeah, so it looks like you've provided a way for a PM to add asserts into my code if they also provide half the implementation as well. If we were trying to implement something like a hash table, this spec description language has to be rich enough to support the ability to add in sets and stuff like this. Is that functionality there?
Okay, so the question is, it looks like a PM should be able to come in and add asserts to your code. Yeah, I would say that's maybe not the kindest characterization, but let's say that it can be used as a common vehicle for communication between developers, testers, and program managers to all agree upon an implementation-independent view of what the component should do. And yes, the whole point is that that should live separately and can be injected against the code at any point in time to check that that code is behaving that way. And yes, we do think ASML in particular is a rich enough specification language to allow you to specify anything you would want about an implementation.
We actually had a tester take the spec and implement his own version of a hash table that was pathetically slow and completely different.
Right.
And he compared that against our current implementation and found a significant number of issues. So this methodology, I think, can actually work.
Sure. In one way, it's just two-version programming, right? Where you're really saying we should have a spec that is easy to understand but perhaps doesn't perform so great, and we should have the real implementation, but they really need to do the same job. So, yeah, I agree. Yeah.
So I really like this work. I'm wondering if I install this thing, does that somehow have to work with VS6, or is there a standalone compiler?
Currently, it has to work as in VS6, I believe.
And if I'm running VS.NET already?
Yeah, no, it's not ported.
So I probably should say this is work in progress. So we have everything implemented for COM and C++ implementation.
I was mostly interested in playing with the language itself and seeing the expressive power of it or not.
Right. So then you can do it. You can just download ASML. You'd have to run it in VS6, and then you can write specifications in there.
So, actually, like in your answer, can you have a VS6 and VS7 coexist?
Yeah,
that's no problem. That's fine.
That's a great theory. Yeah. It's running on a different machine, so it's not.
No. It works just fine. No problems.
Yeah.
It works on my machine.
It works. Sometimes it works. Sometimes it doesn't. My team has had mixed success, and we share stories about how to get it to work. But.
Okay, well, in the coming months, we will have a version that runs on the .NET.
So, Mike, I think one more comment. There's an email alias for ASML.
Oh, well, if they go to that website, yeah.
Go to the website, but that's a good discussion forum. So don't just download it and then have trouble and quit. Download it, have trouble, then email the alias. And don't quit, because actually the bugs are going down pretty well, but there will be some bugs.
All right.
Yep.
All right, and the ultimate talk in this workshop is going to be Trishul Chilimbi talking about using garbage collection to improve program data locality.
Okay, thanks, Todd. So this is work that's done in the context of a larger project called the Daedalus project, and the goal is to improve program data reference locality, whether you have garbage collection or not. But the focus of the talk today is, if you have garbage collection, how can you leverage that to improve data reference locality? So the problem is processors are getting faster at a much faster rate than memory systems. There's a growing processor memory performance gap. It's large today, and it's only going to get larger. So the ubiquitous hardware solution to this problem is the memory cache. It's a small high-speed memory that sits between the processor and main memory and tries to intercept as many accesses as possible. And for the cases where the data reference or instruction reference hits in the cache, performance is not too bad, and things works pretty well. But in the case where things miss in the cache, performance really is bad. And to see that this really does have an impact, I've used hardware performance counters to break down the execution time of some programs, and I've broken it down into busy time and memory stall time, and the memory stall time is just for data references, and other stalls, which are typically branch mispredictions and instruction cache misses. And so you see, for a certain set of programs, like the first set, memory performance really isn't an issue, and everything's fine. But for other programs, memory can be a serious issue, and you can spend a large fraction of your time just waiting for memory. Yeah, Steve.
Those first two are spec marks, right?
Yes.
Most of them do sit in L2 cache, right?
Actually, the Spec 2000, there's about 6 or 7 Spec Int programs that don't sit in the L2 cache. So MCF is one, but there are about 4 or 5 others too. So the spec benchmarks itself are getting bigger that they don't fit in the L2 cache.
Did you try GCC?
Yes, so GCC does fit. Yeah, GCC, the problem there is more branch mispredicts. So that's the background, and I'll give you some motivation for our approach to address this memory performance problem, and I'll talk about how we go about doing that. So if you think about improving memory system performance, there are a bunch of orthogonal things you can do. Well, you can say, I'll completely redesign the hardware, I'll come up with better caches. That's certainly a possible approach. You can say, well, I'll just rethink my software. I know I have this memory issue, and I'll redesign my code and my algorithms. And that's definitely a really great approach, and you can get large benefits if you do that. But the reality is there's like tons of code available, and people are not really going to go through it and change it. So what can we do for legacy code, and what can we do for code that is programmed by people who are not aware of some of these issues? And so our approach is, can we improve the data reference locality of existing software or software that's not written very well for this problem automatically? And so the idea is, let's think of cache-conscious data layouts. And what do I mean by that? So let's say you have a tree data structure here, and what I've shown you there is like the cache layout. So each of these lines there is a cache line, and the tree nodes are going to be distributed in these cache lines in a certain manner depending on the data layout. If you haven't been too intelligent and you just have a random layout of tree nodes, say I'm doing a search of a key in this tree and I'm traversing down from the root, well, what could happen is typically, since I have not paid any attention in how I lay the tree nodes into cache blocks, I could have as many as one cache miss per tree node access. On the other hand, if you're a bit more intelligent and you realize that, well, if I come to a tree node, I'm going to visit one of its 2 children. And if you're more intelligent in how you laid these things out, you could reduce your cache misses, as I've shown on the right-hand side, by a factor of 2, by intelligently placing the data structure into cache blocks. So that could have a large impact on performance, because that's like a 50% reduction in cache misses. So that's nice. How do you go about doing this automatically? So I'm going to talk about now how you can use the garbage collector, especially if you have a garbage collector that copies objects over, to reorganize structures and maybe even split fields to improve the memory layout. And then I'll talk about some limitations about applying this to real large applications, and talk about some solutions to those limitations. So some background on copying garbage collection. So this is just an example, a simple example to show how copying garbage collection works. The idea is you divide your heap into 2 semi-spaces, the from space and the to space. And what you do is you start with certain objects which are called roots. And these roots are objects that you know are live. And they're live because they're in your register set, or they're on the stack. And so you know they're live. And the idea behind garbage collection is you're going to start from these roots and trace all the objects that are reachable from these roots. And those are the set of live objects. You're going to copy them over to the to space. And anything that's not reachable is dead and garbage. And so you can reuse the from space after you copy things over. So let's take this example and say the live objects, the roots are A, C, and E, and I start with root A. I copy root A over there, and then the next thing I do is I update the pointers in this object I've copied. So if I look at root A, the first thing it points to is B, and so as I update the pointer there, I copy B over as well. Then the other thing A points to is F. So as I update the other part of A, I copy F over. So now A is fully updated, so I go to the next object I've just copied over, that's B. And B doesn't point to anything, so when I look inside B and try to update things, what just happens is I don't really copy anything over. Then I go to F, and F points to G now. So when I come to F and I update the pointers in F, I'm going to copy G over there. And G points to A, so when I update G, all it's going to do is update the pointer of G now to point to the new version of A. So I'm done with that link, and I start then with the second root, which is root C. I copy C over. It doesn't point to anything else, so when I update it, it just updates its pointers, which is nothing. And then the final root is E, and so then I copy E over. And so I've copied all the live objects over now, and D is garbage because it wasn't reachable. And I have a nice compact layout, but on the other hand, the layout was kind of driven by the topology of how things were connected, and it's not really driven by how things were accessed temporally. And so the layout, though compact, may not be exactly what you want from a cache point of view. It may not have the right things packed together in the same cache line, for example. Okay, so the idea now is like, okay, we have this garbage collector that copies things over. Let's try and be intelligent and look at how the program is accessing data and use that information and give it to the garbage collector and let it use that to copy things over in a more intelligent manner. And so the idea is, we collect the data reference trace of the program, build some kind of affinity graph structure based on this trace, and then use that to drive how the garbage collector copies things over. So we use a simple object access buffer, and the idea is we have this sequential buffer which we keep adding objects to at each load. So when you have when you load a pointer and you load an object, it inserts the address in this sequential buffer and increments the thing until you come to a guard page where it overflows and fills the buffer again. And so when you're done with this, what you have is you have a sequential trace of object accesses since the last interval and since the last garbage collection interval. And then what you can do is you can use this object access buffer information to build up some kind of an affinity graph of how objects are accessed together. And one simple way of doing this is to use like an auxiliary locality queue structure. And the idea is it's like a simple window that sits over your object access buffer and captures temporal relationships within that window. So say this is my object access buffer, I access A, I put it in the locality queue, and since my object affinity graph doesn't exist, I add a node for A now. I come to B, I put that in the locality queue, and I add edges between everything already in the object affinity graph that were in the locality queue. So my locality queue, well, there's a bug in this PowerPoint. It should have A and B here, and so I add an edge from B to A. Then I come to G, and since G gets added to the locality queue, I put an edge from G to the other two objects in the locality queue, which were A and B. Now I come to A again, and what that does is it bumps A outside the locality queue here, and the two objects in the locality queue now are B and G, but I already have edges from A to B and A to G, so I just increment the weight of the edges here. And it continues in this manner. I add C, and it adds edges to the other objects in the locality queue here, which are A and G, and so on and so forth. So the idea is you build up a graph which captures temporal relationships determined by the size of your locality queue. And then the idea is, well, you have that, and now when you do your garbage collection, can you use that graph to guide how you copy objects over from the from space to the to space? And the idea being the temporal relationships are now going to be captured by putting these objects spatially next to each other, and so you could get better cache performance. So the idea is you have to start with the roots again, and so you pick the root which appears in the object affinity graph, and the sum of the outgoing edge weights is maximum. So if you look at roots A, C, and E, only A and C appear in this affinity graph, and the weight of A, as far as the outgoing edges go, is more than the weight of C. So you start with root A, you copy it over, Now, in the traditional technique, what you would do after copying A over is you would look at the pointers in A and copy those over. So you would copy B over and you'd copy F over. But now what we're going to do is we're going to use the affinity graph to guide how things get copied over. So after you copy A, what you're going to do is you're going to do a greedy depth-first search of this graph in some sense. And so from A, you can either copy C, D, or F over. But the edge between A and C has kind of the maximum weight. So you copy C over. And now you have two choices. You can copy D or F. D has a higher edge weight, so you copy D over. Now you can copy either G or F over. And G has a higher weight, so you copy G over. And then you copy F over. And so then you're done with the affinity graph, but you're not yet done because you have to make sure all roots and all reachable objects from roots get copied over too. So for example, but before that you want to update the objects, update the pointers within these objects. And so you want to update the pointers in A, and when you do that, B, which is reachable from A but hasn't been copied over yet, will get copied over as you update the pointer in A. And you update the pointers for all the objects first, so C, D. You don't copy any more objects here, but it updates the pointers within themselves, so they're correct. And then you notice that root E, which is a root and is live, is not on the affinity graph, and so you need to copy that root over and anything reachable from it. And so then you're done, and the layout is different from the earlier layout because now you use this affinity graph to guide the layout rather than just reachability properties. Yes?
Is the copy still just a simple tree walk? I understand that it's prioritized now with
Yes.
numbers, but is it still just a simple tree walk?
Pretty much. Yep.
Pretty much, or is?
It is. It is.
Okay, because suppose there were an arc from C to G that had, I don't know, weight. Well, I don't care, any weight. Mm-hmm. Does that mean after you chose to go from A to C, you're committed to going to G then? Because you're at A, mm-hmm. C, the only child it has is, or the only reference it has is to G.
Yes.
Okay.
Yes.
Even though doing that might.
Yes. So it's not a global optimal. It's a greedy algorithm. That's right. That's right. So the constraint is. So that's one of the limitations I'll talk to you about. You can't afford to spend too much time being intelligent because this is happening while the whole program is running. And so there's this trade-off. I want to be accurate, but if it costs me too much, I'll just be greedy and get it done right away. And so you're right. It need not be globally optimal in any sense.
Well, you could have a priority queue, which is relatively efficient, of all the pending things, and then you would. Right.
So there are things you can do to improve this slightly, but you're never going to get like a fully accurate optimal solution in fast type. But there are definitely things you could do. Yeah, I agree. Yes?
Is it true that something has to be dead more than one garbage collection cycle before it's actually not copied to the 2 space?
So that's a good point. So actually, I was going to gloss over that point, but if you look carefully at the previous slide, D actually was garbage. Yeah. And it got copied just because it appeared in the affinity graph, even though it wasn't reachable. And so what happens is you can copy garbage over, but you can only copy it over once because then it's never going to be accessed in the affinity graph again. And the affinity graph is thrown away at each garbage collection point. The other caveat that makes this not a problem is that this kind of technique is only done is not done for the nursery. And most of the garbage is generated in the nursery area. And since we don't do it for the nursery area, it turns out I have numbers that show that the amount of garbage copied incorrectly for this one extra garbage collection is like less than 0.1%. So it turns out not to be a problem. That's a good point, though. Okay, so does this work anyway? I mean, it seems like there's a lot of overhead going on here. So how does this really work? So there's a bunch of programs. The first 5 are CSIL programs, if you're familiar with the language. It's an object-oriented language with some similarities to Java. And the last 5 programs are fairly large Java programs. And so what I'm doing here is I'm measuring the normalized L2 cache miss rates. And this is on a Sun E5000. So it's actually on a real machine using the hardware performance counters to measure the cache rates. So these are the normalized cache miss rates. And so you notice for the CSIL programs, you do actually pretty well. The cache miss rates reduced by 20 to like about 40%. For the Java programs, not as well, but still about 20 to 25%. And the reason for this difference in the two programs is Java objects have a larger object header. And so it reduces the number of objects you can collocate in the same cache line. And so you don't get as much benefit as you get for the CSL programs. So one question you can say is, well, you're doing a lot of effort. You're collecting the whole reference trace. Do you really need that information? Can you just do something more approximate and try and improve the layout just with that information? And so there's previous work on doing page-aware kind of layout in which the garbage collector uses more imprecise information, and rather than doing a breadth-first traversal of object reachability, there's a depth-first traversal. But it turns out that doesn't really help for improving cache performance. And the reason is fairly obvious. I mean, in a page you can put multiple objects together, and so if you're right on a few of them, you get better performance. Cache lines are pretty small. You can typically collocate just about 2 or 3 at most. And so you better be exactly right. Okay? And so then the other question is, does this actually translate into execution time improvements? Because that's just cache miss rate. Who really cares? And the answer is it actually correlates fairly well. You get almost very similar improvements in execution time for the cache-aware scheme, and really not too good improvements for the page-aware scheme. And so you really need to do something at the cache level. So the next step is, okay, this works pretty well for CSL programs, but not so well for Java programs. And the reason is that you have these objects, and typically what happens is you just access certain fields of the objects, and not the whole object. And so the problem with co-locating the object is you also co-locate a lot of useless information when you put them in the same cache line. And so it would be nice if you could split the object. So you split the object, and in some sense you just keep the hot fields of the object and somehow extract the cold fields out of the object. And that would kind of reduce the effective size of the object and allow you to co-locate more in the same cache line. And so you could definitely reduce your cache misses by a large amount if you could co-locate the reduced objects. So that's what we did. It's profiled field accesses, figured out which were the hot fields of structures, and removed the cold fields, placed them in a new structure, and then fixed up the code in the compiler to make sure that this all works correctly for accessing cold fields. So this is kind of the process. You instrument the program, get the profile, figure out the hot fields, get the compiler to modify the program so you have split these structures. And then you do the thing I told you earlier where you trace the references, build the object affinity graph, give that to the garbage collector, and use that for doing the layout. And so how well does this work? So I've just shown you the execution time improvements now for the Java programs. So this is the original numbers before the splitting of hot and cold fields. And so when you split the hot and cold fields, you get a further about 5 to, I think, 25% improvement additionally over the others. So overall, when you apply both techniques, the improvement in execution time for these Java programs is fairly impressive. It's ranging from about 20% to about 34% or so. So that's nothing to sneeze at, right? So what are the problems with this? Well, there's some issues with applying this directly, like to CLR, for example. And one problem is the whole thing works based on this low overhead data reference profiling. You're tracing all these references, and you want to make sure the overhead of that is pretty low. And to make that happen, there are a couple of things. First of all, it requires reserving a register. And that works on Sun, but it doesn't work on x86. You really can't afford to reserve a register. And if you don't, then the overhead goes up too high for this technique to work. The other reason it works is it doesn't really track all loads. It only tracks loads to objects that it guesses are going to live long enough that they don't die in the nursery. And the way it does that is with some compiler analysis. And that can be sometimes inaccurate. And so there's some issues there. Then the other issues are the object affinity graph. Todd already mentioned some limitations. You have this approximation of temporal relationships. It's a greedy algorithm. And if you want to do better, you can, but there's this trade-off. The higher accuracy, greater processing cost, and so there's problems there. So what you'd really like is, a fast, accurate way of doing this layout. So that's what I'm going to talk about now. First, I'll start with the low overhead data reference profiling. So the first way to make profiling low overhead for something like that is to do sampling. It makes sense. Sampling works pretty well. So let me just sample some of the references. The problem is I need this temporal information. So I need to sample bursts. I can't just sample individual references. What I need to do is turn on sampling for a while, sample a whole trace of references, stop, and then continue, and so on and so forth. And so that's what basically this does. It builds on some work done by Arnold and Ryder for doing low overhead profiling. So we extended it a little bit to do temporal profiling of bursts. So the idea is, say this is your original program, and what we're going to do is we're going to build a copy of your original code, and we're going to, all method entries and loop back edges are going to have an additional check on them, okay? And what happens is when we come to one of these checks, we're going to decide, do we want to go to version 1 of the code, which I call the checking code, I'll explain what that is, or do we want to go to version 2 of the code, which is the instrumented code, and we make this decision at every method entry or back edge. And so what the checking code really does is it's the original code with just these checks for saying, you know, which one do I want to go to the instrumented code now? So the checking code is very low overhead. It's almost no overhead except for these little checks. And the instrumented code is the high overhead code where all the load references are traced. Okay. So typically what happens is when you sample, most of the time you jump to the checking code, and when a timer goes off, then you jump to the instrumented code, stay there for a while, collect a burst, and then come back to the instrumented, to the checking code. And so it turns out that, you know, with 0.1% sampling rate, we can get high enough accuracy for these temporal data reference sequences. And at this sampling rate, the overhead is less than 5% for all of the benchmarks. And it's probably going to be less in the CLR environment because the base case we used here was highly optimized x86 code. And so the overhead will probably be less in the CLR environment, but we have to wait and see. Yeah. Steve?
Did you, when you computed that 5% average, were any programs in danger of having cache effects because of their text size? Or were they all small code?
SQL Server probably was in danger of having cache effects, but
so what was the number for SQL Server?
The number for SQL Server was like, I think, 4.6%. It was on the high end.
So I was just wondering because it's like you're essentially doubling the code size.
That's right. You're doubling the code size, but the thing is whenever you execute in the instrumented code, you're going to be a lot slower because of these cache misses in particular. So the thing is, the checking code is pretty much in your cache. Okay, it's the instrumented code because it's executed so infrequently that's outside your cache and which you get cache misses on. And so, you know, the reason why it's not a huge impact is because, you know, your sampling rate has to be pretty low to allow you not to spend too much time in that. But you're right.
Do you have any idea how that overhead, is it a lot of it having to do with cache misses that you're taking because you're fetching in a bunch of new code? Or?
A lot of it is cache misses and branch mispredicts because now you're branching there.
Thank you.
Yep. Okay, so that's the low overhead data reference profiling, which allows us to get partly there. And then the next thing is how do we determine the data layout accurately and fast and not rely on these object affinity graphs and imprecise kind of measures. And so before I get to that, there's this abstraction I call hot data streams, which I believe allows us to get that. And so what's a hot data stream? A hot data stream you can think of is as a sequence of data object references that appear consecutively all the time. Okay? So if this is my data reference stream here and A, B, C, D are different data object references, if I analyze the stream, I notice that ABA and CEF are hot data streams because, you know, they appear often and they appear in the same order many times. Okay? And so it's hot because it appears often and it's regular, that is, it repeats very often, so it's pretty stable. So one way of thinking about these hot data streams is they're kind of analogous to hot program paths in your program. You're accessing exactly the same paths in your data structures. And so if you can identify these hot data streams, and it turns out, you know, a small number of these cover over 90% of all data references, then what we can do is just use these hot data streams to do the layout. So the question is, can we detect these fast? And if so, then we can use it to do the layout. And so the thing that allows us to detect this fast is a compression algorithm called sequitur. And I'm not going to go into the details. I'll give you references at the end of the talk, and you can look at them if you're interested in pursuing that. And the idea is it takes a reference stream of data references. It detects these hot regularity. It's a regularity detector in some sense, and it detects objects that repeat often. It builds up a representation, and that representation can be analyzed pretty fast to find these hot data streams, or these sequences of data objects that appear consecutively very often. And it turns out the algorithms for doing this are very fast, they're linear time, and when we do it on the sampled data that we get from this low overhead data reference profiling infrastructure, it takes like a few seconds from getting the set of references to getting the set of hot data streams. And they're very precise because they're completely accurate in some sense for the set of information you have. And so then the idea is, you have this information now, use that, give it to the garbage collector rather than these object affinity graphs to determine the layout when it copies things over. So that's the to-do thing. We're not at that stage yet. But so the summary is, like cache-conscious layouts can offer very large benefits. And the garbage collector can really be used for doing a lot of this. It can do structure layout reorganization. It can split objects into hot and cold portions. And I believe it's practical within the context of CLR because, we have this low overhead technique for doing data reference profiling. And we have a good, fast, accurate way of determining the data layout. And this last thing is like a controversial statement I always like to make. I really believe that, as processors get faster and faster compared to memory systems, and given the fact that it's much easier to do kind of data reorganization optimizations in languages like C# compared to languages like C and C++, at some point we're going to come to a point where these kind of optimizations allow languages like C#, which permit garbage collection and other techniques that allow us to do data reorganization pretty easily, to approach and even perhaps exceed the performance of C and C++. So future work, well, got to implement and evaluate this in the context of CLR. That's something that's ongoing. And if you're interested in references for a bunch of what I talked about, for the GC stuff, there are 2 papers. For the low overhead profiling, there's one submission we're currently working on. It should be out there in a few days. And the fast, accurate data layout determination, there's a paper on that. And everything's kind of reachable from this link here. So stop with that, and any questions? Yep, Gideon?
I would point out that NT does a little bit of random sampling tracing anyway because of the way it maintains the working set. But getting information reliably out of NT would have to ask favor from the...
So they sample what? Page faults?
They have soft faults, so they know which byte got a page into the working set again. Not that the page is in the working set.
Yeah, I actually
and they throw this information to the garbage can currently.
And actually, I was talking to people in Intel, and apparently the P4 too is going to have some sampling where they actually have a buffer that's going to store the addresses of objects that missed in the cache. They're going to have a history buffer. That's right. So yeah, I mean, there's more and more information.
It's easy to get favor from NT, but from Intel it's impossible.
Well, they said it's already in there, so I didn't ask them for it.
But they won't let you see it.
They won't give you an instruction to...
That's right.
No, they won't.
Right.
More questions?
Thanks.
So I just wanted to say thank you everyone for coming. It's been